So by my clock, it's time to start. I believe that there was supposed to be a chairman for this session, but he doesn't seem to be here. So I think I will just go ahead. No. I'm going to be talking about the arrow impossibility theorem. I am not counting on you necessarily knowing what the arrow impossibility theorem is. I will explain what it is, but if you do happen to know, then that's so much the better. There's a long literature on the subject. I think this is a small enough group so that I will encourage you to ask questions as we go along. I'm going to be building up a step-by-step argument, and if you lose the train of thought, then you will be lost for the rest of the talk. So do interrupt and ask if there's something that you cannot follow. So actually over 70 years ago, the economist Kenneth Arrow introduced the concept of a social welfare function. A social welfare function is a mapping which takes individual preferences over alternatives to social preferences. So think of a voting system, for example. There are a number of candidates. Those are the alternatives. Each citizen or each voter has preferences over these candidates, so each voter has a ranking. And the idea of a social welfare function is that we take the profile of individuals' preferences for these candidates into a social ranking. Now, it may sound a little bit strange to think that society has preferences over candidates or alternatives. That's not what Arrow really meant. The idea of a social ranking is essentially a contingency plan. That is, suppose that society has to choose one of these candidates for a particular office. Well, it may turn out that their favorite candidates is not available for some reason. There may be a feasibility issue. In that case, we would go to the second candidate on the list and so on. So the idea of a social ranking is just to provide a backup plan if the original plan doesn't work. Now, Arrow's central finding, theoretical finding, was what we now call the impossibility theorem, which says that if there are three or more candidates, there's no problem with two candidates. With two candidates, you can take a vote and go with whatever the majority prefers. So two candidates is easy, but once you have three or more candidates, then there is no social welfare function which satisfies four conditions which seem very reasonable and not too demanding. And I will describe what those conditions are. They're called unrestricted domain, the Pareto principle, non-dictatorship, and independence of irrelevant alternatives. Again, don't worry if these names don't mean anything to you. I will explain what they are. So the unrestricted domain condition just says that the social welfare function should be defined for whatever preferences individuals turn out to have. we may not know in advance what rankings are possible for individuals, so we have to define the social welfare function on an unrestricted domain of preferences. That sounds very reasonable, and it is very reasonable. The Pareto principle, it's sometimes called the consensus principle, says that if every citizen or every voter prefers candidate X to candidate Y, then society should rank X above Y. Again, that seems entirely natural. It would be very perverse if we had a social welfare function where everybody thought X was better than Y, yet we ranked Y above X. The third condition is called non-dictatorship, ND for short. And this is also a very reasonable condition. It just says that it should not be the case that there's a dictator. A dictator is someone who always gets her way regardless of what everyone else thinks. So if the dictator prefers X to Y, then X must be ranked above Y socially, even if everybody else prefers Y to X. So clearly, for important social decisions, the idea that only one person's preferences matter is not very appealing. All right, so these three conditions are, in fact, very weak, and they're satisfied by just about every social welfare function that you can think of, any social welfare function used in practice or studied in theory. Here's an example. In many countries, including the United States, the most common social welfare function is what is called plurality rule. In plurality rule, you look only at individuals' top-ranked alternatives. So it's as though each person is just voting for one candidate. And then you rank the candidates according to how many top-ranked positions they have. So the winner, the top rank, the candidate that's ranked first will be the candidate that's ranked first by a plurality of the voters. The next candidate will be the second biggest total, and so on. It's easy to check that plurality rule satisfies these three conditions. And as I said, just about every other method of aggregating preferences is going to satisfy it as well. But the final condition, yes. Oh, yes, yes. Yes, thank you. That is a misprint. This word should be than. Yes, thank you. I'll rely on you to catch mistakes like that. It'll keep you awake after lunch. Okay, so then we come to the final condition, which is called independence of irrelevant alternatives. And unlike the first three, practically no social welfare function satisfies IIA. IIA says the following. It says that when we're determining the social ranking of X and Y, we need to look only at individuals' rankings of X and Y, and not how they rank some third alternative Z. Now that sounds pretty innocuous, but it's not innocuous. It rules just about everything out, and that's why Arrow derived this impossibility theorem. One example of a social welfare function that does satisfy IIA is what is sometimes called majority rule, or Condorcet's method. It was advocated for by an 18th century mathematician, Condorcet. According to majority rule, we rank X above Y as long as a majority of people rank X above Y. And notice that by definition, this satisfies IIA because any third alternative Z doesn't figure in the ranking. But this, unfortunately, majority rule violates the unrestricted domain condition because we will not always get a well-defined social ranking according to majority rule. This was something that Condorcet himself pointed out. This is Condorcet's example where 1/3 of the voters have the ranking XYZ, 1/3 have the ranking YZX, and the remaining third have the ranking ZXY. Notice first that that candidate X cannot be ranked first because a majority of voters prefer Z. These voters prefer Z to X, and these voters prefer Z to X, and that adds up to 2/3. So X cannot be ranked first. But Z cannot be ranked first because a majority prefer Y to Z. These voters prefer Y to Z, and these voters prefer Y to Z, and that's also 2/3. So that means that Z is not ranked first. But Y can't be ranked first because a majority prefer X. These voters prefer X to Y, and so do these. So notice that we go around in circles. Z is preferred to X, Y is preferred to Z, X is preferred to Y. There's no well-defined social ranking. That's the problem with majority rule. By the way, this is called the Condorcet paradox, that majority voting doesn't lead to a coherent social ranking. So the fact that it's so hard to satisfy IIA, of course, is an argument against it. But nevertheless, there is, I think, a compelling justification for IIA, which is that it rules out what we call vote splitting or spoilers in elections. And to illustrate what I mean by that, I'd like to use a particular example. Forgive me, I'm going to use an American example. I'm an American myself, and so I'm particularly interested in social welfare functions used in the US. I want to use an example drawn from the 2016 American presidential primaries. Now, I'm sure you'll recognize one of the names up there. I think that accounts for your reaction. The other two you may not have heard of. So Donald Trump, you may recall, was actually elected president in 2016. But before he was elected president, he had to get the nomination of the Republican Party. And there were what we call primary elections to determine who would be the Republican Party nominee. And two of the other candidates for nomination were Marco Rubio, who was and still is a senator from Florida. In fact, it's conceivable that he might be Trump's vice presidential running mate this year. We don't know yet. And then John Kasich. John Kasich was a former governor of the state of Ohio. There are actually many other candidates as well, but these three, Trump, Rubio, and Kasich, were just about the most important. And if I added in the other candidates, we'd be getting very similar qualitative results. So I'm leaving them out for simplicity. So let's imagine a scenario where the population of Republican voters broke down into three groups. There was one group with the ranking Trump, Kasich, Rubio, and then these other two groups supporting Rubio and Kasich. As I said a few minutes ago, in the US, we normally use plurality rule to determine who wins an election. So in an election like this, Trump wins because 40% is bigger than 25 or 35. So Trump is the winner. Trump is ranked first, then Kasich, then Rubio. But you may perceive a problem with the idea that Trump should win this election because actually a majority of voters prefer Kasich. These voters prefer Kasich to Trump. These voters prefer Kasich to Trump, and that adds up to 60%. So from that standpoint, it looks a bit strange for Trump to be the winner. Now, why is Trump the winner? Because Rubio is spoiling the election for Kasich. Rubio is taking away support from Kasich that would have gone to make up a majority of support for Kasich. And so Rubio causes vote splitting to occur, spoils the election for Kasich, and that ends up leading to Trump winning the election. Now, one nice property of IIA, independence of irrelevant alternatives, is that it prevents a scenario like this from occurring. And to see that, let's look at a second scenario. This is exactly the same as the first scenario, except that for this middle group of voters, Rubio, who was ranked first, is now ranked last. But that's the only change. Everything else is the same. Now, let's look at this second scenario. In this second scenario, it's obvious that Kasich should be ranked above Trump, right? Kasich is ranked first 60% of the time. He's ranked second 40% of the time. For Trump, it's just the opposite. So it's obvious in scenario 2 that Kasich will be ranked above Trump. And in fact, just about any voting method, any social welfare function you can think of will rank Kasich above Trump. But if the social welfare function satisfies IIA, then Kasich has to be ranked above Trump in scenario 1 as well, because notice that when we go from scenario 2 to scenario 1, everybody's preference between Kasich and Trump is exactly the same. It's only this irrelevant alternative Rubio who has changed positions. Everything else is the same. So IIA says that if we rank Kasich above Trump here, we have to rank Kasich above Trump in the first scenario. So that shows in particular that plurality rule, this very common voting method, violates IIA. Well, that I think is actually quite a compelling justification for IIA, because really ranking Trump above Kasich in scenario 1 doesn't seem quite right. However, I'm going to argue that IIA is overkill. That is, yes, it does rule out spoiler effects, but it's stronger than necessary for ruling out spoilers. And furthermore, by imposing IIA, we make it impossible to take into account how strongly voters feel about one candidate over another. I'll explain what I mean by that in a minute. So let's, to illustrate what I'm just saying about preference intensities, let's go to another scenario, scenario 3. This is not such an exciting scenario because we're not talking about Trump anymore. We're talking about X, Y, and Z, but you can put in some names if you like. Here there are two groups of voters. One group has ranking XCY, and one group has ranking YXZ. Now I want to look at a particular voting rule, particular social welfare function called the Borda count. So I mentioned Condorcet before. Condorcet was a French mathematician in the late 18th century. Borda was also a French mathematician in the late 18th century. They were both members of the French Academy of Sciences, and they both wanted to improve the election method in the French Academy of Sciences. Condorcet argued for majority rule, which I already talked about. Borda argued for what we now call the Borda count. Under the Borda count, if there are 3 candidates, then voters rank the candidates, and every time a candidate is ranked first, she gets 3 points. Every time she's ranked second, she gets 2 points. Every time she's ranked third, she gets 1 point. We then just add up the points, and we rank the candidates in order of their point totals. So if we do that for this profile, to get X's Borda total, we first look at where X is ranked first. X is ranked first 45% of the time, so X gets 3 points from all these voters, so it's X times 45. X is ranked second 55% of the time, so X gets 2 points from those voters, and then X is never ranked third, so X has a grand total of 245 points. Let's do the same thing for Y and Z. If you do the arithmetic, and let's hope I've done it right, Y ends up with 210 points, and Z has 145 points. So the social ranking is X, Y, Z. In other words, X wins. If X is not available, then Y wins. And, That's how the Borda count works. Now, let's once again change the scenario a little bit. And in going from scenario 3 to scenario 4, once again, I've just made one change. It's to the first group of voters. Up here, Z lies between X and Y. Now we've moved Z down to the bottom. Well, this turns out to change the social ranking of X and Y. Up here, X was ranked above Y. Now, Y is ranked above X. Why does this happen? Well, in scenario 3, X is ranked 2 places above Y for all these voters. So X gets 2 points more than Y for all these voters. But in scenario 4, X gets only 1 point more than Y for these voters. And that's enough. That's a big enough difference to change the social ranking. So now Y beats X. Now, this is a violation of IIA because, once again, in going from scenario 3 to scenario 4, nobody's ranking, no individual's ranking of X and Y has changed. So IIA says that we should rank, if we rank X above Y here socially, we should rank X above Y here socially. The Borda count doesn't do that, and so it violates IIA. Nevertheless, you can argue that the rationale that I gave a few minutes ago for why we might want to insist on IIA doesn't really apply here. Remember, in the Rubio, Trump, Kasich scenario, Rubio was taking away support from Kasich. Let me go back. In scenario 1, Rubio is taking away first place support from Kasich, splitting the first place vote with Kasich. In scenario 3, Z isn't ranked first at all. So it's not as though Z is splitting support with Y. So the argument I was giving before in favor of IIA doesn't really apply here. Furthermore, you might try to make the argument that Z's position relative to X and Y gives us important information about individuals' preferences between X and Y. Notice that when Z lies between X and Y, that may lead us to conclude that these people have a strong preference for X over Y, because the difference between X and Y seems pretty big, with Z in between. In this case, where X and Y are adjacent in an individual's ranking, the preference intensity for X over Y may not seem to be so strong. Now, I've been talking very loosely here. I need to formalize what I've just said, but the idea is that we may be able to infer something about intensities from voters' ordinal rankings. But IIA, the problem with IIA is that it prohibits us from making use of that information in the social ranking, because IIA says we can't look at any third alternative, Z, in deciding how to rank X and Y. So how do we formalize what I just said about preference intensity? Question. At the moment, I'm not giving any reason for that. Uh, I will give you a theorem later on which implies that you have to give those weights, but at this point, no. The Borda count is just an example. There's no reason why the weights couldn't be 7, 7 to 1 or 13, 5, 4, something like that. That's right. But we will get the linear weights later. Okay, so let's try to formalize the idea that we can infer something about preference intensity from ordinal rankings. So the idea is this. We all know from introspection that there is such a thing as preference intensity. After all, there are some choices we feel strongly about. There are other choices that we feel less strongly about. We know that from our own individual psychologies. That doesn't mean that anybody else can directly observe our intensities, though. So let's assume that we represent intensities by what are called utility functions. So u of x, u of y, u of z are numbers which correspond to intensities. And we know what those numbers are individually, but no one else can see them. Let's imagine that the social welfare function, or the voting rule, is chosen before we even know what the candidates are, the alternatives are. Well, if we imagine that the utilities that I experience, or that you experience, are drawn from some underlying joint distribution, P, the fact that the voting rule is chosen before we know what X, Y, and Z are implies that P must be symmetric. Probabilists use the term exchangeable. P must be an exchangeable distribution because if we permute X and Y, for example, that's not going to change the probability. Okay, so let's assume that the only thing we know about the underlying distribution P is that it's symmetric, so exchangeable. Then let's compute the conditional expectation of u of x minus u of y. First, conditional on z being between x and y, and then conditional on z not being between x and y. It's not hard to verify, it's a simple computation, that this conditional expectation is bigger than this conditional expectation. So that means that in any particular specific situation, it may not be the case that just because we have the ranking x, z, y, an individual has a more intense preference for X over Y than if the ranking is X, Y, Z. But on average, saying that the first situation leads to higher intensity will be correct. So we're talking about expectations rather than being correct in every single instance. This is the formal sense in which we can make inferences about intensities based on rankings or ordinal information. So that's what I'm going to rely on. But as I say, if we insist on IIA, we can make these inferences, but we can't do anything about reflecting the inferences in the social ranking. The social ranking prohibits us from using this additional information. So this leads me to the idea that perhaps this IIA condition is too strong. It's too strong for two reasons. It's too strong first because it's stronger than necessary to rule out spoilers. And it's also so strong that it rules out the possibility of taking preference intensities into account. So let's propose a definition of IIA, a weaker definition, which allows us still to rule out spoilers and also to take preference intensities into account. Yes, yes. This is included in the setup. So how do we include the French situation? Well, let's suppose that, so for those of you who may not be familiar with what France does, they have a two-step French election for president, actually for every office. People first vote over the set of candidates that are initially running. If somebody gets a majority of first place votes, they're really only just voting for one candidate, that candidate is elected. If no one gets a majority, then the two top vote getters face each other in a runoff. But we can collapse that into a one-step election by looking at their rankings. Again, if someone is ranked first by majority, she wins right away. If no one is ranked first by majority, we take the two top candidates, the two candidates with the most first place votes, and we compare them. We can do that because we already have the rankings. Yeah. Yes, no, that's right. If people change their mind, we would need something a little bit more elaborate. But yes, that can be done. This is a little too simple to take that into account, but yes, it can be done. Okay, so what about modified IIA? What does that say? It says that if we look at two scenarios, two profiles, and in both scenarios, each individual ranks X and Y the same way in both scenarios. And furthermore, each individual ranks the same number of alternatives between X and Y. So we can make the same inferences about intensities in both scenarios. If both of these conditions are satisfied, then and only then can we conclude that the social ranking of X and Y must be the same. So notice that this is a weaker condition than ordinary IIA because we're imposing another premise. And so, so now with modified IIA, we can make inferences about intensity. In fact, it's not hard to show that what I'm calling modified IIA is a necessary and sufficient relaxation of IIA for making cardinal inferences. It's necessary in the sense that we have to relax IIA at least this much if we're going to take into account intensity. And there's no point in relaxing it further because we can't make any additional inferences about intensity if we do relax IIA simply on the basis of ordinal rankings. Remember, I compared those conditional expectations before. There are no other comparisons that we can make, just assuming that the underlying distribution is exchangeable. That's the only comparison we can make. Okay, so that is my motivation for modified IIA, and it's easy to see that modified IIA, although it's weaker than regular IIA, still rules out spoilers. If we go back to our original Trump-Rubio Kasich scenario, if Kasich wins here, then according to modified IIA, Kasich still wins here because, remember, the only difference between these two cases is that Rubio, who's ranked last here, is now moved first. So we haven't changed for any individual the number of alternatives between Kasich and Trump. And now I have to talk about a few other axioms, which are all very weak. The only really strong axiom in this whole talk is IIA and its modification. All of the other axioms are weak. What are the other axioms? Well, one of them is called anonymity. This was proposed by Kenneth May, who was interested in crystallizing why, in the case where there are just two candidates, two alternatives, it's so natural to use majority rule. Why do we think that majority rule is the right method for the two alternative case? Well, May showed that majority rule is the only method that satisfies three very appealing axioms. One is anonymity, which just says that if we permute the individual's preferences, that doesn't change the social ranking. Another way of putting this is to say that all individuals count equally. It doesn't matter who the individuals are. It only matters what their rankings are. Another axiom that majority rule satisfies is neutrality. Neutrality says that we should treat all candidates equally. Or formally, if we permute the alternatives so that X becomes Y and Y becomes Z and Z becomes X, then we should, and so everywhere that x appears, we put in y, and everywhere that y appears, we put in z. Then we should permute the social ranking in the same way. So that if before we did the permutation, x was ranked above y, then after the permutation, y should be ranked above z. That formal condition translates into, we have to treat all alternatives symmetrically, equally. And then the third condition is positive responsiveness, which just says that if we change a profile so that x rises relative to y in some individual's rankings, then if x was previously ranked above y socially, it's still ranked above y socially. And furthermore, if x and y were previously tied socially, now x is strictly preferred to y socially. So those three conditions are very natural and very weak. Again, they don't rule out many voting rules that we're actually interested in. And then there's one final condition, which is called consistency. Consistency says that if we take a population and we divide it into subpopulations, then if each subpopulation has the same number one alternative socially, if x is number one in each subpopulation, then if we put the subpopulations back together again, x should be number one for the union of those populations. That's actually a very strong, that sounds weak, but it's actually a very strong requirement. I'm not going to use the strong version. I'm going to use what's called ranking consistency, which says that if in every subpopulation the entire ranking is the same, not just the top alternative, but the entire ranking is the same, then when we put the populations back together again, we take the union, we have the same top alternative. That's a weak condition in the sense that it's satisfied by just about every voting rule used in practice and used and studied in theory. So now finally we get to the main result, which answers a question that was raised a few minutes ago about the Borda count. If we want our social welfare function to satisfy the axioms I've been talking about, unrestricted domain, anonymity, neutrality, positive responsiveness, and ranking consistency, and most importantly, modified IIA, the other conditions are weak, modified IIA is the important one, then we must be using the Borda count, where the points we assign are linearly descending. 3, 2, 1 wouldn't matter if we used 5, 4, 3, but the point is that there's a linear relationship. Now I don't have enough time to fully prove this for you, but I can give you a pretty good idea of why it's true in the remaining time. I have about 10 minutes, I think. So in the case where there are two alternatives, this theorem is uninteresting because in the case where there are just two alternatives, the Borda count is the same as majority rule. And in fact, just about every sensible voting rule is the same as majority rule for the case of two alternatives. The only interesting case is where there are three or more alternatives. So let's concentrate on the three alternative case. And I'm going to even look at a special case of that. I'm going to assume not that, so there are six orderings, strict orderings of three alternatives, but I'm not going to look at all six. I'm going to restrict attention to just three, x, y, z, y, z, x, z, x, y, and that choice is not made arbitrarily. You'll recall that that was precisely the case where majority rule ran into trouble. That was where we got the Condorcet paradox. And I want to look at the Condorcet profile. So for this profile, we saw that for majority rule, we had to have a social ranking of x above y, because a majority of voters, these voters and these voters, prefer x to y. But let's suppose that our social welfare function satisfies the axioms that I've been talking about. Then I claim we have to have social indifference between x and y. And the argument for that is actually very straightforward. Suppose it were false. Suppose we got a strict ranking, x over y, for this profile. Well, now let's use our neutrality axiom. Neutrality says that if we permute the alternatives, we have to permute the ranking in the same way. So let's look at the permutation where x goes into y, y goes into z, z goes into x. Then our original profile becomes this, right? So x, y, z becomes y, z, x, and so on. And the original social ranking, x over y, becomes y over z. Now let's apply the same permutation again. And we get this profile and this ranking. Okay, so that's using neutrality. But the next observation is that from the standpoint of the anonymity axiom, which says that we treat all voters equally, these three profiles are all the same, because all we've done in going from here to here is to permute who has which preferences. Here, the XYZ preferences are held by the first group. Now they're held by the second group, and so on. So really, these three profiles are the same from the standpoint of anonymity. So that means that any inference that we make about the social ranking, x over y, y over z, z over x, has to apply for this profile, because this profile is not any different from this or this. So that tells us, if we put these inferences together, that we have x over y, y over z, z over x, which contradicts the idea that we have a well-defined social ranking. So in fact, our hypothesis that x was ranked above y socially must have been false, and so we have to have social indifference. But if we have social indifference, now we can use the modified IIA axiom. So let's say we have proportions A, B, and 1/3 for these three rankings. We know that when A equals 1/3, B equals 1/3, we have social indifference. But the modified IIA says that as long as A plus B adds up to 2/3, we still have to have social indifference because these two rankings treat X and Y the same way. X is ranked above Y, and there's no alternative between X and Y. So it doesn't matter what A and B are as long as they add up to 2/3. Furthermore, we can now use the positive responsiveness condition to say that if A plus B adds up to more than 2/3, we've taken weight away from YZX, and we've assigned it to XYZ or ZXY. We've shifted preferences away from Y over X toward X over Y. Positive responsiveness says that we have to make the same shift in our social ranking. Since X and Y were tied before, now X must be preferred to Y. And we can go in the other direction to say that if A plus B adds up to less than 2/3, then we have to have a strict social preference Y over X. But if you think about it for a moment, you'll see that we've now entirely characterized our social welfare function. For any profile, we can use the analysis that I've gone through and determine what the social ranking of X and Y must be. Furthermore, that ranking must coincide with the Borda count. Why does it, quote, coincide with the Borda count? Because let's calculate the Borda score for X. X is ranked first by a proportion A, so it gets 3 A points from those voters. It's ranked second by a proportion B, so it gets 2 points for those voters. And the remaining voters rank X last, so that's 1 minus A minus B times 1. So that's X's Borda score. We can also calculate Y's Borda score. And we see that the X Borda score is higher than Y's if and only if A plus B is more than 2/3. So we have indeed characterized the Borda count, at least in this special case. But generalizing to the full domain is pretty straightforward as long as we use the ranking consistency axiom. Remember, the ranking consistency axiom says that we can go from subpopulations to the whole population. It's not hard to show that at any point where we have indifference according to Borda scores, the profile of preferences can be decomposed into these four. In other words, the profile will be a convex combination of these four profiles. These four profiles are all symmetric, and so we can use exactly the same argument that I just went through for the Condorcet profile to show that we must have indifference between X and Y for these four profiles. We then use ranking consistency to put them together and conclude that we have indifference for the overall profile. And that's the idea of the proof. And I've run out of time, so let me stop there.
Thank you very much, Eric. Okay, I'm sorry I was late. I'm supposed to be the chair of this session, but I was not assigned to have a plate, to have a registration.
Oh, gosh. Oh, no.
Anyway, so Professor Eric
This is Dao Kui Li, by the way.
Tsinghua University. Okay, and truly my honor to be here. To actually supposed to welcome and also listen to your presentation. Professor Eric Maskin has had a wide spectrum of contributions to knowledge, ranging from this very abstract social choice or social welfare,
right,
to what we call applied theory, to issues of economies and Chinese economy, like enterprises continuing getting subsidy from banks, even if they're losing money. So truly, it's our great honor to here. And we don't have time, right, for questions?
You know, I'm willing to stay. If you're willing to stay, I'm willing to stay and take questions, but you may want to go someplace else. So you're excused if you want to leave, but those who want to stay can ask questions.
Sure. Why don't we have formally allot 3 questions, then we can do it on one-on-one basis.
Okay.
Right? 3 questions lumped together, right? In the back first.
I'm sorry?
Strategic voting.
Yes, that's a very good question. I did not talk about strategic voting here at all.
So I want to ask, like, is there some comparison, like, did this Borda account, did it encourage or disencourage strategic voting, and different of result of strategic voting compared, say, plurality vote? Because I can think of some scenarios, say there are 4 candidates, A, B, C, D, and A, B are very popular, and the C, D are very unpopular.
Right.
But say the supporters of A would think they don't want to.
We understand. Yeah. Okay. The second question. Let's come together. Second question.
Yeah.
Please. Yeah, so I wonder what is the practical implications. Whether you want to support the system to be implemented. Okay. Yeah. Practical implication. Yeah.
Good question.
Third question.
Oh, actually, yes. So I didn't even have time to get to there. You might have seen on a slide that the word continuity does appear. I didn't talk. There is a continuity axiom. Continuity axiom says that if we change the preferences a little bit, we won't change the social ranking very much. Again, that's a very natural condition. In the special case I showed you, we didn't need it, actually. So I didn't talk about it. But for the more general case, we need the continuity axiom as well. Yeah.
Wonderful. Maybe a quick question.
Yeah.
Before we lump it together. Just go back to the question how you set the score. How you set the score.
Right. Okay. So.
All these questions, let's come together.
Okay. So let me first say a word about strategic voting. So strategic voting says that perhaps voters are not going to want to submit their true rankings because, say they prefer X over Y over Z. So they prefer X most. They're worried, however, that Y might beat X. So they might strategically rank Y below Z, even though they actually prefer Y to Z. That's strategic voting. And in the Borda account, yes, indeed, you might want to do that. So in answer to the second question, what is the practical implication of this? This is, I think, a very strong argument in favor of the Borda account in situations where we're not particularly worried about strategic voting. When might we not be worried about strategic voting? If, for example, the votes are public and so that you are identified with your vote, it's going to look bad if you vote strategically. Everyone knows that I prefer Y to Z. So if I put Z above Y, everyone knows that I'm really cheating by doing that. So this is an argument for using the Borda count when there's not much worry about strategic voting. Now, in political elections in the United States, the voting is secret. And so strategic voting then does become important. In a separate paper, I argue that the Condorcet method is a good method. The majority rule method is a good method for those elections. So in other words, there's not a unique answer to what voting rule you should use. It really depends on the situation. In some cases, it's Borda. In some cases, it's Condorcet. And then the final question was about the points why should the points have a linear relationship? And that follows from the modified IIA condition. Modified IIA says that when we're comparing X and Y, the only thing that matters is how many alternatives are between X and Y. But it doesn't matter where X and Y are in a voter's ranking. X and Y could be at the top, the bottom, in the middle. We get the same social ranking of X and Y in all three cases, which means that the point weights have to be linear. That's where the linearity comes from. Okay, thank you.
Thank you very much. That's a special treat from Aaron Maskin, the 207 Nobel laureate for economics. Thank you, Aaron. Thank you.
My pleasure.